Good evening. Welcome to all of you on the fifth lecture of this series. It's my pleasure to welcome my good friend Felix Finster of the University of Regensburg in Germany. Felix studied physics and mathematics at Heidelberg University before joining ETH Zurich for his PhD. And subsequently, he was a postdoc at Harvard and then researched at the Max Planck Institute in Leipzig and obtained his habilitation from Leipzig University before taking up his current professorship in the mathematics department at Regensburg. Felix has worked mainly on mathematical problems in general relativity and quantum theory. And in particular, he has developed the theory of causal fermions, which is a candidate theory of unification. And Felix has also authored several books, most notably The Continuum Limit of Causal Fermion Systems, from Planck scale structures to macroscopic physics. And Felix likes to fondly refer to this as the Blue Book. It's a big, comprehensive volume. And Felix kindly invited me to spend a week at his university last year. And since then, we have been collaborating and looking for common grounds in our approaches to unification, and especially the role of octonions. So today we here for the theory of causal fermions and octonions. Over to you, Felix.
Okay, great. Thank you very much. First of all, thanks a lot to the organizers, to Tejinder and Michael, for inviting me here. It's really a great pleasure to give a talk in this lecture series. And well, the purpose of my talk is twofold. First of all, I will give an introduction to causal fermion system for, well, people who are not experts in this topic, or maybe have never heard of causal fermion systems before. And then I want to build a bridge and explain the connections which I see to octonions. First of all, in brief, well, what is a causal fermion system? So this is an approach to fundamental physics which involves a novel mathematical model of space-time. So which means that we have a notion of a quantum space-time, a generalized space-time, and the physical equations are also formulated in these generalized space-times. And different limiting cases have been worked out. First of all, the continuum limit, in which you get quantized fermionic fields interacting via classical bosonic fields. And then there's also the quantum field theory limit, where one gets fully quantized fermionic and bosonic fields. And I should say this last point is ongoing, and I will mention a bit more towards the end of the talk. Well, and in this talk, of course, I can't cover all of it. So therefore, if you want to have a more complete picture, overview, more details, I can recommend you our websites where you find papers, books, videos, a whole online course on causal fermion systems. Okay, here I want to begin by asking a general question, namely, which space-time structures are fundamental? Of course, this is a kind of personal question, so where everybody has different opinions. Probably if I asked, let's say, 10 people here in the audience, I would get 10 different answers. And that's fine. On the other hand, ultimately, one wants to formulate quantum gravity. So the question is like, depending on which starting point you take, how is it possible to describe all known physical phenomena plus quantum gravity? So this is the ultimate goal. Good, and my personal preference is what I will now take as the hypothesis, namely I consider quantum mechanical wave functions as the basic physical objects. So just one particle wave functions, in fact, quantum field theory will come a bit later. So therefore, we have a wave function psi, which describes a quantum mechanical particle. For the moment, it's just a wave, no point particles. And I assume that this wave function is there even if I do not make a measurement, and that it has a certain dynamics. So you can take an equation like Schrödinger equation, Dirac equation, a collapse model, whatever you prefer. And this then gives the dynamics to this system of wave functions. Good. Now, if I want to describe this a bit more mathematically, I'm led to considering a vector in the Hilbert space. And now you might object, well, the vector in the Hilbert space itself is not supposed to be the physical object because there's the phase freedom. I mean, the phase of the vector has no physical significance. This is why often in the quantum mechanics course, one learns that the ray generated by a vector, this is really the physical, this is what describes a quantum mechanical particle. One should go even a step further. There's also local gauge invariance. So if you transform the phase of a wave function locally, and at the same time, you also need to transform the classical electromagnetic potential, then this is again the symmetry transformation. In other words, the local phase also has no significance. Instead, only the absolute value, this is the quantity which we should consider physical, because this is the probability density of the quantum mechanical wave function. Good, so therefore we are led to considering the absolute square of all quantum mechanical wave functions of our system as the basic physical objects. And if you do this, then the question is, well, suppose we know all these absolute squares of all wave functions, what does this tell us about the underlying space-time structure? Can we infer what the causality, metric, fields, and so on are? And well, in other words, we want to probe our space-time by looking at the absolute square of the wave function. And I should say, just to make things conceptually clear here, by probing, I do not really mean like a measurement process where the system is changed, no collapse of the wave function. Instead, this is more like a mathematical device, if you like, in order to get information on what is going on in space-time. Let me try to explain a bit more precisely what I have in mind. First of all, I do this in Minkowski space. I mean, curved space-time. I will say a few words later. For simplicity, let's just take Minkowski space. And then we consider, say, a scalar particle, again, for simplicity, for example, Klein-Gordon field, if you like. And then we consider the absolute square. And in the first step, I want to allow for the preparation of an initial state at a certain time, t. So this means, just one second, okay. So this means like if here plot time and space and time, and I have here an initial data surface t equal to t0, I choose a certain initial configuration. And now I let the system evolve in time, then due to finite propagation speed, I know that the wave is identically equal to 0 here on the left and on the right. So it's only non-zero in this future dependence of the initial data. And in this way, I can find out what the causal structure of my space-time is. One can go on and say, for example, how can I detect an electromagnetic field? What I can do is something like here in this picture here, I consider two wave packets. One of these wave packets travels through the region where the electromagnetic field is. Then this wave is scattered. And then later on, I can kind of measure how the wave looks like in this region here. For example, by polarizing, by taking certain linear combinations of psi1 and psi2, looking at their absolute values and so on. Okay, this is, of course, just to exemplify this. But the general message is if you allow for preparation of suitable initial data, then you can basically recover the whole space-time structures, all the fields and particles and so on. But now let's go a step further. Suppose we do not allow for preparation of an initial state. So I do not want to modify my system in any way. I assume that, well, there are a certain number of wave functions flying around, and I can only use those for making my observation or for probing space-time. And in this situation, probing still works, provided that there are sufficiently many wave functions around. This is what I try to plot here. Suppose we have, in this example here, 4 wave packets. They are already there. And then I just consider how do they overlap, how do they evolve in time, and this gives me some information on space-time. Not on all of space-time. For example, if I take a region here where all the wave functions vanish, then I cannot detect anything, then I don't know how space-time looks like in this region. Okay, and the general lesson is, I mean, the more wave functions there are, the more information we have on space-time. You can also call this as a certain space-time resolution or bandwidth in a more information theoretic language. So this is kind of such concepts is what you want to use. And now you might wonder, well, suppose you want to describe, we have vacuum, then there are no wave functions, then we have no information on space-time, or how is this supposed to work? And an important ingredient here is that we work with this Dirac-sea picture. So we take Dirac's idea of a sea of particles seriously. So we describe the vacuum not just by empty space, but there is this filled sea of Dirac particles. So therefore, even in the vacuum, we have plenty of wave functions, which we can use for probing space-time. Okay, I hope this explains a little bit what we want to do. Now let me formalize this idea, and doing this leads us to the mathematical setting of causal fermion systems. How can we make this, how can we make this idea, or this probing idea, mathematically precise, and how can we really find out what we can do with this probing? To this end, let's just consider a finite number of wave functions in Minkowski space, finite just for simplicity. And we assume that these wave functions are vectors in the Hilbert space, just an abstract Hilbert space. And for simplicity, we orthonormalize these wave functions. So then we have a finite dimensional Hilbert space, and all the vectors in this Hilbert space are wave functions in Minkowski space. Good, and now we introduce a basic object, the local correlation operator. And this works as follows. So we take a space-time point x, and then we evaluate two wave functions, say psi j and psi k, at the space-time point and multiply them together. So here the bar is simply complex conjugation, so just multiplication of complex numbers. And then we get a complex number here on the left side, and j and k are free indices. So therefore, in total, we get an F cross F matrix. And the diagonal entries of this matrix, these are just these absolute squares, which we had at the very beginning. And so they tell us about the densities of the particles. And the off-diagonal matrix entries tell us about the correlations of the jth and kth wave function. And well, generally speaking, I mean, this matrix, this contains all the information which we can get by probing at this specific space-time point x. If you don't like to work with matrices, you can also do this abstractly as follows. So on our Hilbert space, we have like two inner products. One is the Hilbert space scalar product, and the other is the point-wise inner product obtained just by evaluating at one point and multiplying together. And then one can express one of these inner products in terms of the other using and this gives a unique linear operator on the Hilbert space. You could say this is the signature operator of this representation. And if you now write out this linear operator as a matrix in our basis, then you see the matrix entries are precisely these matrix entries which I wrote down here. Okay, so this is the local correlation operator. And well, it is a Hermitian, this matrix here is Hermitian, which you see right away by taking the complex conjugate and interchanging j and k, or the corresponding linear operator is a symmetric operator. And moreover, this operator has rank at most 1 and is positive semi-definite. And this can be seen immediately by writing it in the form E star E, where E is the evaluation operator, which just maps the Hilbert space vector to the wave function at one space-time point. And since this here maps to one-dimensional space, this operator E has rank at most 1. Consequently, this operator E star E has rank at most 1 again, and is also obviously positive semi-definite. Okay, so what have we gained now? So let me just draw this. I mean, first of all, we call the set of all linear operators of rank at most 1, which are positive semi-definite. Let's denote them by curly F. And then to every point of Minkowski space, so here we have Minkowski space, to every space-time point, we can associate the corresponding local correlation operator, which is then a point in curly F. So we get a mapping from Minkowski space to curly F. And now we denote the image of this mapping by M. So there's a distinction between this script M or curly M. So this is the classical space-time Minkowski space. And the ordinary M here, this is now a subset of curly F, so a set of linear operators. Okay, and they have to be, well, it's important to distinguish between them because what we have on the right side, this really contains all the information which can be retrieved from the wave functions, all the information which we can get by probing in the way I described it at the very beginning. And now we want to consider the objects on the right as the basic physical objects, because as I said at the beginning, I want to consider these wave functions as the basic objects and only the information contained therein. This is what should make up space-time, and this is really how physics should be formulated. So therefore, we want to forget about the left side. We want to disregard the objects on the left. So we no longer want to work in Minkowski space. We want to disregard the causal structure. We don't want to work with Dirac spinors anymore. Instead, we want to work exclusively with the objects on the right. So just with a subset of this set of linear operators. Okay. So far, so good. So this is not quite the end of the story, because one important structure is missing. Namely, what we need is also a volume measure on space-time. And here by measure, I simply mean we want to know what is the volume of subsets of space-time. Let me make precise what I mean here. So we had this mapping F, which maps Minkowski space to this subset of curly F. And now we want to give this subset here an additional structure. So we want to endow it also with make it to a measure space. So we want to introduce a measure. And this measure is denoted by rho. And mathematically, we take the push-forward measure. In case you don't know what the push-forward measure is, it's very simple. Suppose we take a subset omega here on the right side. Then we take its pre-image here, f to the -1 of omega. This gives us a subset of Minkowski space. And then we could take the usual space-time volume of this set. And this gives us a certain positive number. And this is the measure of the subset of curly F. So this is how this works. And now we have already, again, now we drop all the structures on the left. And now we have a bit more structures because on the right side we have a measure, and it turns out that the image of this mapping F can now also be retrieved as a support of the measure. In fact, not quite, because the support is the closure of the image of F, but maybe that's not so important now. Good, so therefore we can now kind of also forget about this set M. Instead, we just take the measure rho. Its support gives us M, and that's it. I mean, we don't want to use more structures. And this is almost the setting of causal Fermion system. So therefore, let me now give you the general definition and explain what the difference is to what we had before. And then I will give you an example, namely the example of Dirac spinors in Minkowski space. So here's like the abstract definition. So we start with the Hilbert space. And then there's a parameter n, referred to as the spin dimension, just a red natural number, 1, 2, 3. Now we consider the set curly F of linear operators with the properties that they should all be symmetric. They have finite rank. Well, and symmetric means we can diagonalize them. We have real eigenvalues. And then we can count how many positive and negative eigenvalues are there, always counting multiplicities. And we consider only those operators which have at most n positive and at most n negative eigenvalues. And finally, we have a measure rho on F. So this is the general definition. And it is similar to what we just had in the example, except that in the example, we didn't have any negative eigenvalues. We had operators of rank at most 1 and positive semi-definite, which means we have at most 1 positive, but no negative eigenvalues. This is the only difference here. And the reason is that this is needed in order to describe spinorial wave functions. And let me explain now how this works. And this is also like a kind of model example of basic example. And once it's clear how this works, then you will also understand at least in principle how things work in curved space-time and so on. So therefore, let's go through this in detail. So we could start now with Minkowski space. We consider the free Dirac equation. So just no interaction right now. This psi here, these are these usual 4-component Dirac wave functions. And on those, one has an inner product, which we call spin inner product, which physicists usually write like this, like psi bar phi with the adjoint spinner phi bar. And the point is that this inner product is not positive, so it's not a scalar product, it's an indefinite inner product, and it has signature 2, 2. This is because this matrix gamma 0 has 2 positive and 2 negative eigenvalues. And this signature has nothing to do with the signature of space-time, which is, of course, here 1, 3. So this is just like the signature of the inner product on the spinners at a given space-time point. Good. So then we can form the probability density. I mean, I prefer to write it like this to make sure to clarify that this is really like a 0 component of the vector. And integrating this over space defines a scalar product, and this is the usual scalar product used in quantum mechanics. If psi is equal to phi, then this integrand here has interpretation as a probability density. And it is independent due to current conservation, in other words, as a consequence of the Dirac equation. Taking this scalar product, we get a Hilbert space. And now we choose the subspace of this Hilbert space. And this has to be, the subspace can be thought of as the space of all the occupied wave functions. So if you want to describe the vacuum, you take all the negative energy solutions. And now we can mimic the construction before with this local correlation operator, except that on the right side, we have to take the spin inner product. And since the spin space has now dimension 4, we get an operator which is symmetric, has rank at most 4. And since this inner product here has signature 2, 2, we get at most 2 positive and at most 2 negative eigenvalues. Good. And here maybe I was a little bit too simplistic. I mean, if you have a finite number of wave functions, everything is fine. If you take an infinite number of wave functions, then it might be that you cannot evaluate point-wise, that this here is not well defined, and one has to regularize. And I mean ultraviolet regularization. For example, you can then smear out the wave function on a small scale, for example, by mollification. And this is the purpose is, this is what this regularization operator is good for. So it maps the Hilbert space vectors now to continuous wave functions. And then you can use the local correlation operator as before. And this is important because the certain length scale comes into play, namely the length scale of this smearing of this regularization, and this can be associated with the Planck length. Okay, and after doing this, we are in a similar setting. Curly F are now all the linear operators of rank at most 4, which have at most 2 positive and 2 negative eigenvalues. We have a mapping from Minkowski space, now again to a subset of this new curly F. We take the push forward measure of the volume measure in Minkowski space, and this gives us the measure rho, and in total, we have a causal Fermion system of spin dimension 2. And again, we dropped all the Minkowski space structures. We only want to work with the structures here. I should say that for simplicity, I just did it in Minkowski space. It works similar in curved space-times and a globally hyperbolic spin manifold. Good. Now, you might wonder, well, how can one formulate physical equations in this setting? Of course, this is crucial. And you can't do this in the standard way. There's no way you can write down a differential equation anymore because we dropped all these structures. So what can one do instead? And maybe just to give you the intuitive picture, the idea is to have equations which tell us that all these wave functions organize themselves in such a way that this Dirac configuration is a minimizer. And now suppose you want to describe an interacting system, well, then these wave functions again organize themselves, but in such a way that they all satisfy the Dirac equation with one potential in here. And this potential then serves as the definition of the bosonic potential, of the electromagnetic potential, for example. So in other words, on the fundamental level, there are only the fermionic wave functions. And the bosonic potentials are used just as a device in order to describe the collective behavior of all these wave functions. Okay, this is just to give the intuitive idea. Now, how does this look like mathematically? I mean, it's not so important, in fact, for the remainder of the talk, but I think I thought I should still show you how this goes. So this works as follows. So suppose we take now 2 points in curly F. So these are 2 linear operators, symmetric, rank at most 2n, at most 2n positive and at most n negative eigenvalues. Now we can multiply these 2 together. This gives us a new linear operator, which has again rank 2n, but which is no longer symmetric. Namely, if we take the adjoint of x times y, well, then we have to flip them around. Each of them is symmetric, so we simply get y times x. But the operators do not commute in general, so this is why this is not the same as x times y. So now we have a non-symmetric operator of finite rank, so we can still compute the eigenvalues, including algebraic multiplicities, and they will in general be complex. So now, I want to point out, in view of this non-commutativity of these operators, we get complex eigenvalues here. Good. And now we take the Lagrangian is formed by taking the absolute values of the eigenvalues, taking their differences, squaring it, and summing over all the eigenvalues. This gives a non-negative number. And now we integrate this Lagrangian over both arguments, over x and over y, and rho. This is the measure in the abstract measure in the causal Fermion system, in the definition of the causal Fermion system. Now, this is a non-negative number. We can minimize this under variations of the measure rho. And then one has to also take into account certain constraints, which make sure that everything is mathematically well-defined and that you get non-trivial minimizers. Okay, but maybe, as I said, the details are not so important here. Let me therefore move on and make a few general remarks. First of all, I mean, in this theory of causal Fermion system, there is just one basic object, namely the measure rho. And this is a measure on a set of linear operators on the Hilbert space. And this measure describes space-times as well as all objects therein. And an underlying structure is a family of fermionic wave functions. I mean, if you just think of how we started or how we got to this measure, we used a family of wave functions. And in fact, starting from rho, you can also get a family of wave functions back. So therefore, this is kind of an important underlying concept. And these wave functions, as I said, they describe everything. In particular, they encode the geometry of space-time. So you could say meta encodes geometry, or since these wave functions are quantum mechanical objects, you could say this is a quantum geometry. And what I also wanted to point out, I mean, this causal action principle describes space-time as a whole. So you just have a measure rho, which describes all of space-time. You vary this measure. In other words, you vary all of space-time. And then you find a minimizer, which gives you the whole space-time. This is similar to the Einstein-Hilbert action in GR. It's a nonlinear variation in principle. This is again similar to Einstein-Hilbert action or classical field theory. Nevertheless, one gets a linear dynamics in certain limiting cases. Okay, just to get the general mathematical structure here. And now I wanted to compare it also with non-commutative geometry, because I'm often asked, well, the ideas seem a bit similar to non-commutative geometry. What is the connection? And also, like discussing it with Tejinder last year, we also talked about the spectral action principle in non-commutative geometry. So therefore, let me try to give you a brief comparison. Well, first of all, I mean, there are similarities, in particular, both in non-commutative geometry and causal Fermion system. We don't start with space-time, but space-time emerges from more fundamental structures. In non-commutative geometry, this is this non-commutative algebra, this spectral triple with the Dirac operator. Causal Fermion systems, this is this measure on the set of linear operators. So therefore, many ideas and general concepts are really similar. On the other hand, when you go to the more details, it is really quite different. And let me try to summarize the differences from my point of view. Well, one difference is that, well, in non-commutative geometry, there's a Dirac operator or generalized Dirac operator, which plays a central role. Instead, here, the Dirac operator is no longer important. Instead, only the wave functions are the central objects. In other words, specific solutions of a Dirac operator, if you like. And the advantage of working with these wave functions is that you can generalize it. The wave functions no longer need to be solutions of any Dirac equation. So this is like one major difference. So this is why we work with this wave function instead of with one underlying operator. Moreover, the setup of causal Fermion system is Lorentzian. So right from the beginning, I mean, this is why it's called causal Fermion systems. I mean, the idea is really to describe space-time, which have a causal structure. And this causal action principle is really designed in order to describe space-times. In contrast, non-commutative geometry works, or has so far been made to work mainly in the Riemannian setting, and even there only on compact manifolds. There are attempts to do it Lorentzian, but at least this was not the main purpose, and it's not obvious how to do it. In particular, now when it comes to more technical comparison, in non-commutative geometry, there's the spectral action principle, where one considers the eigenvalues of this Dirac operator using heat kernel expansions, typically near the diagonal. And well, in this heat kernel expansion, and this is also the eigenvalues, the spectral decomposition of the Dirac operator, this is something which works only in the Riemannian case. In causal Fermion systems, we work with this Lorentzian version, and from the technical point of view, it's quite similar, because instead of the heat kernel expansion, we consider the light cone expansion. So again, an expansion for small distances, but now for small Lorentzian distances, which means an expansion near the boundary of the light cone. Okay, and also on a more technical level, I mean, these heat kernel expansion and light cone expansion are really quite similar, but then the way they enter the actual, well, the action itself is then formed in a quite different way. Okay, maybe we can discuss this later in case you want to know more. Maybe I should better move on in order not to get, well, let's see. Well, here's another way of interpreting things. I mean, often I'm asked, well, how can I think of these linear operators? What does this mean intuitively? And one way of understanding is that these are possible events. So the operators in curly F, these are possible space-time events. And then when I choose a measure and I could take its support, then I distinguish a subset of possible events. This is the set M. These are then the events which are realized in our space-time. And space-time is made up of all the realized events. And the physical equation relates all the events to each other. So this L of xy then relates x with y, and these are two space-time events. And in fact, it turns out that this interpretation as events goes beyond this just ordinary language picture. Namely, there is Jürg Fröhlich developed what he called the ETH approach to quantum theory. So this ETH stands for events, trees, and histories. And he has a very precise mathematical definition of what he means by an event. And it turns out that the space-time point operators in causal Fermion systems also fit into this mathematical setting. If you want to see this in more detail, this comparison, you can look this up in this paper. Okay, now let me, well, but before going to the Octonions, there are a few more things I want to explain just to give you a bit more complete, although very rough picture of how this causal Fermion system approach works. Namely, I mean, I dropped many structures, and the question is, are they gone or are they still here? Are they still there? And it turns out that they are kind of encoded, although in a somewhat hidden way, in the causal Fermion system. And this is why we call them inherent structures. So let me explain a little bit how this works. And to this end, it's good maybe to start with a completely abstract general causal Fermion system. So suppose rho FH is a causal Fermion system. Then what can you do? First of all, we take the support of the measure, which gives us a distinguished subset of linear operators. This is what we call space-time. And a priori, there are not many structures. I mean, these are just points. But there's one additional structure, namely these points are linear operators. So the space-time points are linear operators on the Hilbert space. And this contains a lot of information and gives rise to many additional structures. For example, if you take now a space-time point, you can compute the eigenspaces of the operator. Or if you have two space-time points, you can multiply them together, compute the eigenvalues, the corresponding eigenspaces, and so on. And it turns out that doing all this systematically, and one recovers, or one gets quantum objects like spinors, wave functions. One gets geometric structures, connection curvature, and one gets also causal structure and analytic structures. So in other words, one gets all the structures one really needs in physics. And all these structures, they correspond to the structures which we have in a classical space-time. Suppose I go to these examples which I showed you earlier, and I take a certain limiting case where the number of wave functions goes to infinity, so the dimension of the Hilbert space tends to infinity, then all these objects here go over to the usual structures in Minkowski space on a Lorentzian manifold. So therefore, all the structures here really generalize the usual notions to a setting where the usual notions no longer exist. I mean, even in settings where space-time is discrete or where space-time has a weird microstructure, even in such situation, you can still speak of wave functions, causal structure. I have well-defined Euler-Lagrange equations. I have objects in space, densities, and all of that. Okay, and of course, I mean, it would take too much time to explain you all this in detail. I mean, I have a few backup slides, which we might come back in the discussion in case you are interested in that. Here, I just wanted to focus on the causal structure because this is this is why it's called causal Fermion system. And this works as follows. Suppose we take now two space-time points, or 2 points in M. We again multiply these operators together and compute the non-trivial eigenvalues, just as we did earlier when I showed you the Lagrange. Since these are complex eigenvalues, we can distinguish different cases. Either these eigenvalues all have the same absolute value. In this case, we call the 2 points space-like separated. Or the eigenvalues are all real and do not all have the same absolute value. In this case, we call the points time-like separated. And in all other situations, we call the points light-like separated. So we have here a very general and abstract notion of causality, which at least is compatible with the causal with the causal action principle. Namely, if we, here's again the Lagrangian, if we have 2 points, space-time points, which are space-like separated in this sense, then the Lagrangian vanishes, and the Lagrangian is also minimal. So here, if 2 points are space-like separated, the Lagrangian vanishes, and it turns out if you look at the corresponding Euler Lagrange equations, these 2 points do not interact with each other. In this way, kind of a very general notion of causality is built into the causal action principle. Well, and as I said, now if you go back to the system in Minkowski space, then this causal structure really gives you back the usual causal structure in Minkowski space, which is not at all obvious and which is something you need to check out in detail. Okay, in fact, there's also a distinguished time direction. Just to complete the picture here, there's a functional which is real valued and anti-symmetric. And then the sign of this functional can distinguish whether y lies in the future or in the past of x. However, the resulting relation lies in the future of is not necessarily transitive. In other words, there could be closed causal curves, both on a microscopic scale and on a macroscopic scale. Good. So now I wanted to tell you a little bit about quantum spacetimes before going back to classical spacetime and to the Octonions, of course. As I said at the beginning, the idea is that causal Fermion systems really describe fully quantized systems. And the question is, how should this work? And the classical picture, I mean, this is very impressionistic here. I mean, is as follows. So suppose we have a classical spacetime, as in the examples I showed you earlier. In this case, the support of the measure was just a 4-dimensional submanifold or subspace of curly F. So just some 4-dimensional object. The quantum spacetime, on the other hand, should be described by a measure whose support is much larger, as it's shown here. So it's like a thickened. So the support is thickened, or in other words, you have many transverse degrees of freedom. So it's indicated here. So M, this script M is again the classical spacetime. B are kind of some internal degrees of freedom. And the spacetime of the causal Fermion system is this product. Now, if you integrate with respect to this measure rho, you also integrate over all these additional degrees of freedom. And this has similarities to a path integral. So in other words, integrating over rho is not only integral over space-time, but also integral over field configurations or whatever you have in mind. And more specifically, now you ask yourself, well, how can one describe, for example, entangled macro states? Of course, a typical example is Schrödinger cat, superposition of a dead and of a dead cat and a living cat. And to understand this, one should keep in mind, or it's important feature, that everything is really non-smooth on a small scale. So this is how you can think of as the support of the measure. So it could have discrete parts, it could have continuous parts, but everything is in a very non-smooth configuration. And then, for example, the dead and the live cat, they are somehow contained in this measure. Okay, I mean, this looks maybe a bit like science fiction, but in fact, it is not. I mean, we have worked this out. I mean, this picture has been made precise in a few papers. More precisely, where are we here? So, I mean, we can construct a quantum state at any time t. So in other words, we can really, out of this complicated measure, we can extract information which which is then encoded in a quantum state, or can be described by a quantum state, say in Minkowski space, on the algebra of observables, which are just the usual observables which one has in quantum field theory. We also showed that this description allows for general entanglement. So in other words, I can write you down in detail how this superposition of this dead and alive cat, how the corresponding measure looks like. And what the last step is to work out the dynamics of the quantum state. And the hope is that this, or I mean, it is, well, let's say, I mean, we are optimistic that what we will get is linear dynamics on Fock spaces up to small corrections. So this means we get like a quantum field theory in a certain limiting case, and the corrections then should even account for physical phenomena like collapse of the wave functions. Hopefully, this is what we are aiming for. But we are not here yet. I mean, this is what we did so far. Good, and of course, I only have limited time. I think now it's really good to move on to the continuum limit, so the simpler limit, which is worked out in this blue book, which Tejinder already mentioned at the beginning. So they're setting, so the general idea is as follows. So we start with causal Fermion system. So this is an abstract mathematical framework where we have quantum geometry, we have this causal action principle. And now we want to take a certain limiting case where we get into the usual usual physical language, usual equations. Then we want to get Dirac fields, strong and electroweak gauge fields, gravitational fields. In fact, we also get all this on the level where the fermion fields are second quantized and the bosonic field is classical. And well, how does this work kind of schematically? So what the input is, okay, this is again the blue book. I mean, so the input is the vacuum. So we have to say, how does the measure describing the vacuum look like? And here we have to also put in a lot of phenomenology. So we have to put in here that we, first of all, that we have Dirac-Cs and that we have several generations of Dirac-Cs. So the beta here goes from 1 to 3, so maybe I should be a bit more precise. So this P of xy, this is a distribution which describes completely filled Dirac-C of mass m beta. For example, the electron vacuum. Now, if we have 3 generations, so for example, electron muon tau, then we take sum of such Dirac-Cs with 3 different masses. So the beta, here's our generation index. And once we have this P of xy, then there is a clear procedure how to get the corresponding measure rho of the causal Fermion system. Good, so this is in this way you can, for example, describe the leptons. If you want to have a system which also involves neutrinos and quarks, then one has to take several copies of this P of xy, and copy here means just direct sum. So this means instead of having, I mean, here we have 4 component spinors, so like 4 by 4 matrices. Now, if we take this direct summons, if we take 2 summons, we have an 8 by 8 matrix, 12 by 12 matrix, and so on. And now we take 8 direct summons. This is important in view of the Octonions. This is why I want to focus or like spend some time on that. So we take, first of all, 7 direct summons, which are all identical. So they also involve the same masses. So 3 masses come up here. And then there's an 8th direct summand, which involves different masses and which also breaks the chiral symmetry, so the left-right symmetry. So in total, so then we have 4 times 8 is 32 components. So this is a 32 times 32 matrix. In other words, the spin dimension is 16, so 16 positive and 16 negative eigenvalues. Now the system has to be regularized on a microscopic scale, so this ultraviolet regularization, which I mentioned earlier. And we have to build in by hand that this last direct summand breaks the chiral symmetry, so the left-right symmetry. Good, and now, so as I said, this is the input. Now we take this and analyze the causal action principle. And then it turns out that these 8 direct summands, they form pairs. So then we have 4 pairs. And this is what we refer to as spontaneous block formations. And these pairs are blocks. And then these gauge groups, they mix these different blocks. And one gets really like the gauge group of the standard model. So U1 cross SU2 cross SU3. The SU3 mixes 3 of the blocks, namely the quark blocks. The SU3 mixes the 2 sectors within each block, and it acts only on the left-handed component, and the U1 is the usual electromagnetic U1. So what we get out, and this is really not an input, so what we get out is really the same coupling as in the standard model. We also find that there are some mixing matrices, and that the SU2 gauge field is left-hand and massive. And moreover, we also get classical gravity. So these are really the results. And of course, I can't tell you in detail how this works, maybe just to give you a flavor, an idea of how this works. So the method is as follows. I mean, if you start with this vacuum Dirac configuration, then this can be written as a solution of a suitable Dirac equation. So this is just the Dirac equation without this B. So just the vacuum set can be written as a solution of a Dirac equation. And now I take this Dirac equation. So this is a mass matrix, which involves all the masses of the vacuum wave functions. Now I put in here a perturbation, which can be completely general, for example, a Young-Mills field, gravitational field, something non-local, whatever. And then the question is, are the Euler-Lagrange equations satisfied if in the limit epsilon to 0? And the Euler-Lagrange equation of the, so in other words, do we have a critical point of the causal action principle? I should have said that this vacuum configuration is a minimizer in this limit. So therefore, we really have the vacuum as a minimizer, and then we can perturb around this and ask the question, are the Euler-Lagrange equations still satisfied for the perturbed system? And the answer is yes, but only, or if and only if this B has a very specific form. Namely, the form I just showed you earlier with these gauge groups and so on. So it's a Young-Mills field corresponding to certain gauge groups, and corresponding classical field equations are satisfied. So this is the procedure. And of course, there's a lot we put in. So we put in how the vacuum looks like. And also we put in that we are in a classical space-time, that the underlying space-time is Minkowski space and so on. But then the form of the interaction comes out. And this is what the continuum limit is about. Of course, you could ask, well, how do more general minimizers look like? Then I would say, well, they look as I showed you before. They are such quantum space-times with entanglement and a complicated structure and so on. So in other words, we cannot expect that the minimizer really has this nice form as I just showed you. So these are very specific, approximate minimizers. Let's put it like that. Okay, now finally, I see I still have a good. So I mean, maybe I'm almost on time. Okay, now the connection to Octonions. And this goes back to Tejinder's visit in Regensburg last year, I mean, where we spent a whole week discussing this, and I tried to understand in detail and try to understand Tejinder's work and try to make a connection. And let me just explain a few things which I hope are understood so far. Well, first of all, the Octonions. So this is a non-associative algebra generated by these 8 generators. Well, and this is also already where the problems start. It's non-associative. On the other hand, the whole setting I showed you before, operators on Hilbert spaces and so on. Of course, you can also form algebras of operators, but no matter what you do, they will always be associative. So how should non-associative algebras come up here? And there is a way out, namely working with this so-called octonionic chain algebra. So let me explain how this goes. First of all, we complexify. So in other words, we take linear combinations of the octonions with complex coefficients. So this is then an 8-dimensional complex vector space. And we still have a multiplication, which is again non-associative. But now we can make this operation associative by always prescribing that we multiply from the left. So in other words, whenever we have products, we put the brackets as I showed it here. And if you do this, then you get something associative, kind of by construction. In other words, if you look at this associativity, A times B in brackets times C, Well, this doesn't exist because it's always A times brackets B times C. And in this way, one gets, okay, I here use, in fact, Colfury's notation. Also, we looked at some of her videos when Tejinder visited. So this is why I stick to this notation here. So this is then, so what we get here is now an associative algebra. And the Octonions act on this algebra. So there's a mapping from the Octonions cross the chain algebra to the chain algebra, where we simply multiply from the left by an additional octonion. Good. And this seems to fit to the causal Fermion systems in the following sense. And I think the easiest connection to make is just to consider the vacuum. And the vacuum, the causal Fermion system vacuum is described, as I showed this earlier before, we have this direct sum of 8 sectors. So we have 8 direct summands. So they generate like a 8-dimensional complex vector space, which we can then identify with these complexified octonions. And then the above action gives us an action of the octonions on these sectors, on these direct summands. In other words, if I multiply by an octonion, then these sectors will be permuted. And, well, according to the multiplication rule of octonions. Okay, now you might ask, well, what's the point of doing this? I think what really makes this interesting is that this is an approximate symmetry transformation. In fact, if we have here these first 7 summands, they are identical. So therefore, if you permute the first 7 summands, this is really full symmetry operation. The last summand here, as I pointed out, is different. I mean, it has this left-right chiral asymmetry. So therefore, if you permute this sector with one of the others, or interchange it with one of the others, it will no longer be a symmetry transformation. But at least it is still an approximate symmetry. And maybe this is the best one can hope for. One can then ask, well, why is this symmetry broken? How does this symmetry breaking mechanism, how does this come about? Things like that. But it is speculation. I mean, at the moment, I can only say, I mean, the octonions act as an approximate symmetry on the causal Fermion system vacuum. And then there is one more thing which I found quite intriguing, namely these 3 generations. I mean, earlier I had a sum of 3 C's. In fact, if you want to work with this Dirac operator, then instead of taking a sum, you take a direct sum. This is what is called then the auxiliary fermionic projector. So then we have a direct sum of 3 copies, 3 Dirac C's. For example, if I just take one sector, say suppose I want to describe only the leptons, I have a direct sum of 3 Dirac C's with different masses. Of course, this should be M2 here, M1, M2, M3. Good, so then we have 3 by 3 matrices, and now these octonions act here. So in other words, what one gets using this idea earlier is that the matrix entries here should be octonion. So octonionic, like a matrix with octonionic entries. And this can be made to a Jordan algebra. So if you now introduce like a certain product, namely like a kind of symmetrized product, a Jordan product on these octonionic 3 by 3 matrices, then one gets the structure of an exceptional Jordan algebra. And well, there's possibly much more. In fact, I mean, these exceptional Jordan algebras, they play a central role in Tejinder's work, and he got like amazingly good match or predictions of mass ratios and working with these exceptional Jordan algebras. And well, we have been discussing this, and it looks quite similar, but there are still a few things which are unclear. In particular, Tejinder always has square roots of masses, and I don't see them coming up here. So this is why I wrote here ... I think there's a lot more to explore, and hopefully all this can be, this connection can be made stronger, and also in this way maybe bring some of Tejinder's results on more, well, give them a more on a better basis, say a more better conceptual basis for all his numerical, or yeah, for all the concrete results he got. Okay, I think this is all I wanted to say, so I'm perfectly done. So thank you very much for your attention. And again, here's our website if you want to have more information. And of course, I'm looking forward to the discussion.
Yeah, thanks, Felix. That was a very exciting review of causal fermions. Very, very interesting. Thank you. So, as you know, the talk is open for questions. And I think David has a comment. David, would you like to go ahead and please read it out?
Is it possible to change my shared screen to the iPad?
Yeah, so that's I have to unmute David. How do I do that? 1 minute, please. I have to just open the chat and unmute. Give me a moment, please.
Okay, can you see my slides again?
Yes, we can.
Okay, great.
So, David, I think I've unmuted you. Please,
Felix, thanks for your talk. I appreciate it. Yeah, I left the point at the end. I just figured I'd mention as a comment that C cross H cross O can be generalized into matrices, and the Freudenthal-Titz construction can be used to apply to it. And my collaborators just put out a paper discussing the 2x2 case, so I just figured I'd mention that. But I had a question for you. I was just curious if these this causal fermion approach, does this relate to the causal set story? Is how similar is that?
Okay,
I'm aware of that development, but haven't followed it as actively.
Yeah, sure. Good question. Of course, I didn't have time to enter this. I mean, first of all, I mean, we get similar structure, so we also have causal structure, but it's not quite the same, because here the causal structure is not necessarily transitive right from the beginning. On the other hand, in causal set approach, you have a causal ordering lies in the future of, which is by definition transitive. Good, now here one can go further and construct cone structures which are also transitive. So if one does that, then starting from a causal fermion system, you can really construct a corresponding causal set. One difference is that the diamonds do not necessarily need to consist of a finite number of points. Usually in causal sets, you say, like, if you take the points which lie in the future of one point and the past of another point, there should be a finite number of points. In other words, usually one considers discrete spacetimes. This is not necessarily the case here. One can describe discrete or continuous spacetimes. So just to summarize, I mean, starting from a causal fermion system, you can get into the setting of causal sets, but the main difference is here you have a lot of additional structures, and you also have this causal action principle, and there is no correspondence to that in causal set theory. So it's a kind of what it is, richer structures or more, well, it's a richer theory, let's put it like that.
Thank you. Tevian, please go ahead, unmute yourself. Please go ahead. Our last Tevian. Only 1 minute. Yeah, please unmute yourself, Tevian.
There we go. I've been trying to unmute myself for 5 minutes. I had to come back and rejoin. Sorry about that. So a technical question, when you were talking about the chains, it would appear to me that there's some ambiguity there, because the representation of Octonions in terms of left multiplication will not be unique. So are you talking about making a chain unique depending on its representation, or are you allowing for different products to represent the same element of the chain?
I see. So I mean, basically, I don't know if I fully understood your question. I mean, so this is how I define the multiplication. And then in this way, the multiplication rule has become unique.
Sorry, are you claiming, are you interpreting a chain to be a different element based on the position of the element, the position and order of the elements that you
now I
list?
understand. I mean, so suppose you take two different chains, but they are the same octonion.
When you multiply them out, yes.
Okay, fine. And I think I need to take them as different elements.
Thank you. Okay.
Okay, great. Jose, please go ahead. Jose, yeah. Please, please go ahead, Jose.
Yeah, can you hear me?
Yes,
Yes.
yes.
Now, yes.
Hi, everyone. Thanks,
Hi.
Felix, for this nice talk. You mentioned a number of quantum mechanical applications of your theory. You mentioned entanglement. Do you also have a mechanism to explain the collapse of the wave function? Something, say, like in GRW theory, for example, Girardi-Rimini-Weber, or any other mechanism of that kind?
Okay, very good question. I mean, this is something we plan to do. I mean, in fact, together with Johannes Kleiner, who you also know, I mean, he was a former PhD student of mine. He is very interested in this problem.
Mm-hmm.
And we also have ideas in this direction. Maybe just to, let's see, explain this a little bit. I mean, one point is that, I mean, this causal action principle is non-linear. So therefore, I mean, we get like a linear dynamics in a certain limiting case, but there will always be a non-linear correction. So therefore, this non-linear term of the causal of the collapse model, there is something like that already. And then the question is now, what about this stochastic term, which is also crucial for the collapse model?
Exactly.
And here the idea is, well, basically you make use of this, what I showed here, I mean, pictorially like this. I mean, so there is a lot of kind of randomness in space-time, or everything is very disordered on small scales. And this is what should give rise to stochastic, should be described effectively by a stochastic term. So this is the general idea. And well, and we have more concrete ideas on how to work this out, but well, we have all been busy, and so far we haven't made it to write our paper on that.
Okay, so essentially it's through the introduction of noise that you want to account for the collapse of the wave function. Do I understand correctly?
Yeah, exactly. And or more specifically, I mean, I wrote a paper just recently where I analyzed the linearized field equations in Minkowski space. And it turns out that there's not just one solution, say a plane electromagnetic wave, but there's really a whole, well, many different fields. And then the idea is that all these fields are really there, so they are around. So they are all this kind of, in order to describe all these fields, one needs to do a stochastic approach. And this should then give rise to the stochastic term.
I see. Thank you.
Okay, thank you. Please go ahead. How do I say your name? Heb? H-E-B?
Sorry, this is my university account. Therefore, the strange name. So basically, I want to continue on this last question. Does the nonlinear terms change the mathematical structure of your theory? And do you also...
I didn't understand.
Sorry, I hope it works better now. So does this change the mathematical structure of your theory? Because you start to work with linear operators in the Hilbert space and linear wave equations. And then if you go over to the Einstein-Hilbert action, you get the nonlinear dynamics. So how does the nonlinear dynamics on the fundamental level go together with the linear quantum theory or the linearization at a certain limit? So is the fundamental theory basically nonlinear, or more basic question, what is nonlinear about the fundamental theory? So which part of quantum theory become nonlinear on the fundamental level, and which part of the mathematical structure do you keep?
Well, I would say on the fundamental level, it's all nonlinear. I mean, this action principle is a nonlinear variation in principle.
Okay.
But then if you consider kind of macroscopic objects, then it's often sufficient to just to consider the linear dynamics.
Okay.
And this is what gives rise to the usual quantum theory.
Okay. So
And also, maybe I should say
sorry.
these this nonlinear term also becomes small due to decoherence effects. You think
Okay.
that you have suppose you take a wave function, you split this up into many components and bring them out of phase.
And then you
When
also
nonlinear term will
okay.
involve many phases and will
Okay.
become small due to interference effect or destructive interference effects.
Okay, so then you have a kind of decoherence from the nonlinear theory to quantum theory, and then an additional decoherence for or decoherence, a tool which you can use to get from the nonlinear and quantum level directly to the classical level.
Yeah, I think the first part, yes. I mean, so like you have
Okay.
the coherence effect, and this is like why you get a linear theory. But then there's still a small nonlinear remainder, which could give rise to a collapse term, the way Jose just asked about.
Okay,
and well, the classical theory in this continuum limit, I mean, there the approach is much simpler. Don't take decoherence effects into account. I just take a classical space-time field, and in this case, I just get the classical equations.
Okay, thank you very much. And just a brief additional question, but I guess it will be hard to answer. As you're working with a causal system, can you avoid the trouble with nonlinearities and wave function collapse? Normally, what spoils the whole idea is that you're really easy in conflict with special relativity or with Einstein causality if you introduce nonlinearities in quantum theory. So my hope would be that because you're starting from a causal approach right from the start, that you can somehow circumvent these problems.
Yeah, I hope so too. I mean, so let's say, I mean, the setup is causal in the sense that if you have points with space-like separation, they do not interact, no matter what.
No matter what. Also, if
Therefore,
you on the basic nonlinear fundamental level.
Yes. So therefore,
okay.
In other words, the nonlinear term cannot lead to superluminal propagation.
Okay. This would be a huge advantage, I would say, for your approach.
Exactly. This is also what I discussed with Johannes, and this is like what motivated us to proceed in direction of these collapse models. But as I said, unfortunately, for the moment, I have nothing concrete results to tell you about yet.
I wish you all the best in your collaborators, but it looks promising, I think. Thank you.
Thanks a lot.
And thank you for the nice talk.
Thank you.
So more questions, please. So I have quite a few things to ask you, Felix, but does this look to you like Steve Adler's trace dynamics? Because you have an action principle, you derive the Euler equation, those are your equations of motion. You never quantize the theory. There is already quantum, right?
Exactly. So this is really, I mean, from this point of view, it's really also similar to Adler's trace dynamics.
Right.
I mean, one difference is that, how should I put it? I mean, this trace dynamics, I mean, all these operators, they do not see each other. I mean, you have sum of traces. And here it is important that, I mean, these different points, they do see each other because I take products of the operators. And this is what enters the Lagrangian. So therefore, there is more, well, you get kind of more relations between the different operators. And this is also what gives rise to the causal structure in space-time.
Yeah, Jose is saying something.
Yeah, as a follow-up to your comment, Tachinder, in Adler's theory, quantum mechanics is emergent. Whereas if I understand correctly, in Felix's theory, everything is quantum already from the start. Because you've played, I mean, you may say, well, I'm taking h bar equal to 1 from the very beginning, and everything is quantum from the start. So I think that makes a fundamental difference.
Yeah, in Steve Adler's theory is pre-quantum. It's more
exactly. That's what I meant by.
You are saying that Felix is quantum and quantum through and through, No, never pre-quantum. Is that what you're saying?
Exactly.
Yes, I would agree with that. Yes.
Yeah.
That's an interesting difference. Both are matrix dynamics, but they differ. That one is pre-quantum and emergent quantum. The other is quantum.
Exactly. That's the point I was trying to raise.
And Felix, in this Lagrangian, now this is your fundamental Lagrangian. It's all that you have. So I would suppose I want to see the unified theory here, unification of the standard model with gravity has already happened because of the way you have written the action. And then you showed us that somehow you get Einstein equations as well as the standard model out of it here. In what way do I know that the unified interactions already here? And what, for example, is your symmetry group? You get SU3, SU2 plus U1.
Well, in fact, this is not, this is a very good question, and it's not easy to answer because one has to do many computations. This is why in this blue book, I work quite hard to get all this out. And what makes it hard somehow is that in order, if you start from this P of xy, and then you want to compute these eigenvalues here, this is already not so easy. You have to take this P of xy, multiply it by P of yx. Maybe I could also write it here. So you have to take this P of xy, what we had earlier, which is regularized, where we have put an epsilon times P of yx. This is then a 4x4 matrix. Say, suppose if you just take one sector, which depends on x and y, and which is very singular on the light cone. Now you need to compute the eigenvalues. These then are these lambda xyi's, and then you have to plug them in here, take the absolute values differences squared, and so on. So this is why it's not so easy to understand directly what's going on. So maybe one way of understanding it, on a, well, not very, on a rough level, say, here always these absolute values of the eigenvalues come into play, and their differences. So therefore, if you minimize what the system tries to achieve is that all these eigenvalues have the same absolute value. And first of all, what is good is there's a phase freedom. So if you introduce gauge potentials, they lead to phases, and phases drop out here. But now it gets more interesting when you consider chiral gauge fields. So like these left-handed SU2 gauge fields, then they they affect only the left-handed component. If you take this chain, then you have one factor is left-handed, the other is right-handed. So therefore, you get phases, and it turns out that these phases do not drop out of the Lagrangian. And this is why you get conditions. So in other words, in order to arrange that these eigenvalues are all the same, you want to arrange a high degeneracy of all these eigenvalues. There are 32 of these eigenvalues. And now you want to have as many as possible to be the same. And this is what leads to the finding that this SU2 gauge field is the same in each block. So we have like 4 blocks. In each block, this SU2 gauge field has to be the same, because otherwise you destroy degeneracies, and then you get very large contributions here. And well, and for gravitational field is a bit the same. If you take the main contribution is just the diffeomorphism, like whatever coordinate change, which again drops out of the action because everything is diffeomorphism invariant. You have to, and the reason why the gravitational field couples to all the particles in the same way is because otherwise these different Dirac-Cs or the singularities, they see different diffeomorphisms, and then the singularity on the light cone breaks apart. So this and so in other words, there's also the gravitational field couples to all the sectors in the same way, which preserves again a degeneracy of these eigenvalues. And then there's this curvature term which comes into play. Then you have to really compute, well, how does here the Ricci tensor come into play? And this is what this light cone expansion is good for. So you compute this distribution in the expansion on the light cone, and you see here there's a certain contribution involving the Ricci tensor. What does it how does it affect these eigenvalues? How does it affect the Lagrangian? How does it enter the Euler-Lagrange equation? And this gives rise to quite extensive computations, unfortunately.
Yeah, if I try to get the sense of why the known symmetries of nature come out, just for comparison, if you look at Cohn's spectral action principle, it is a rewriting of the Einstein-Hilbert action in terms of the eigenvalues of the Dirac operator. And if you invert the spectral action principle, you would know a priori that you will recover the metric and Einstein gravity. And similarly, because the gauge fields are brought in by generalizing the Dirac operator, momentum P goes to P plus EA. Again, knows beforehand that this will come out. And in terms of the Octonion language, we see that, for example, symmetry breaking of E8 has the standard model gauge group. So there one knows why all this is happening. What is the essence of this Lagrange? Because you started with mapping Minkowski space-time to the causal fermion space. And then this is what you have, but then a lot is coming out. So I'm trying to get to the essence of how do I know that all those symmetries are in here?
Yeah, well, it's difficult to answer. Well, I should say, I mean, coming up with this Lagrangian, of course, was not obvious. I mean, it took me a lot of time, and I started with many computations, and I tried many different other Lagrangians, for example,
I agree.
Eigenvalues,
Definitely
and then in the end, somehow taking this, really taking these absolute values and differences squared, this seemed to do the trick. And like in retrospect, I don't really see how, I don't see a really shortcut. I mean, to really say from here I can read off things. I mean, comparing to this Cohn's spectral action, I mean, there is a more concrete comparison. I mean, like if, I mean, Cohn wanted to get this Einstein-Hilbert action. And then he looked at this Dirac operator and the large eigenvalues, in other words, the behavior near the diagonal, the kernel near the diagonal of the resolvent, for example, of the heat kernel. And then one sees that there's a term involving the Ricci tensor. And this term is the same term as what we see near the light cone in this Lorentzian picture. So therefore, the fact that this P of the Ricci, which comes up here, is the same. It's really, if you do some kind of Wick rotation, say, I mean, or go to the Euclidean setting, then this really corresponds to what happens near the diagonal in this spectral action principle.
Because you started with the fermionic wave functions and the correlator made from them. So somewhere the Dirac operator or Dirac equation kind of information is probably gone in.
Yeah, exactly. Like in this derivation, it is gone in simply because I say the vacuum is built up of solutions of the Dirac equation.
Absolutely. Okay, now I get it. So it's very, it's beautiful. It probably would be equivalent to the spectral action principle, as you said, though of course more general, you are Lorentzian, more realistic. But yeah, so now I see the connection. Here the Dirac operator, you have fermionic wave functions used to make correlators and they satisfy the Dirac equation. And probably, so that's where the very interesting. So then that is the reason probably why you anticipate seeing the standard model in a way similar to the spectral action.
No, it's true. This is maybe why the results are similar. I should say that maybe also, I mean, when you take this Dixmuir trace, I mean, what Cohn considers, the idea is, I mean, you concentrate on what happens near the diagonal. And here I concentrate on what happens near the light cone, because this is where the singularities come up. In other words, this is the main, if you take the square here, this gives you something highly singular on the light cone. And this is why you kind of concentrate or focus on what happens near the light cone. And this is also then why this Ricci tensor and Maxwell field and so on, why they really come into play. And I should say, this is also the reason why you can compute things, because on the light cone, there's this method integration along characteristics, which really gives you explicit formulas for everything.
Thank you. Yes. So one other question is, in the P of XY, at some stage you had 8 sectors. 7 were identical, the eighth one.
Sure,
But
maybe let me go
yeah,
back. Yeah. Let's see, this was here, I guess. Yes.
right. So it's, I wanted to know why 8?
Okay, well, so the reason is as follows. I mean, first of all, we form pairs. So this is kind of the isospin pairs. So then starting from 8 sectors, you get 4 blocks, 4 pairs. And then 3 of these pairs, 3 are identical, have 3 identical pairs. And this is where the color SU3 acts on. So the
No,
color
so
SU3 mixes.
Oh, sorry to interrupt you. Is it that then I'm using some a priori knowledge of the standard model already here, that there are, quarks have 3 colors, and there are 3 up quarks, 3 down quarks, and the neutrino and the lepton?
Well, only as if you think the total number here is the number 8. This is an input. And the point is, of course, I mean, that 8 is, I mean, let me just see, why can I not write? Okay, yeah. So, I mean, 8 is 2 times 3 plus 1. I mean, this is what comes into play. I mean, then the 3 here, this is what color is. So these are the color SU3 mixes these 3. Then these are the leptons. And these 2 here, this gives you the isospin.
This is an input, is it?
Well, the input is only what I had here. I mean, that these basically like that these 8 form 4 pairs. This comes out.
Because here's when Colfury does it from the Clifford algebra CL6, she will get this 8 out. She didn't have to put anything 8 in. The 8 just comes out because these octonionic chains have a maximum 3 independent length. I mean, the maximum independent length is 3, and then if you just act on the generators, you just get 8.
Okay. Well, I mean, no, that's reasonable. I mean, if you start from octonions, then you have the number 8 already. And then if you say, well, these octonions then corresponds to what here I call a sector, then you have 8 sectors right from the beginning.
Yeah, of course, we could ask there why octonions. That nobody knows the answer. The octonions, because they seem to work. I mean,
exactly. Also, like here, you could ask, well, why 8? I mean, this is, of course, an input. I mean, if I had taken 6, then I would have gotten something completely different. And also, I mean, I wanted to point out, I mean, it's really important that one of these direct summands is distinguished. Namely, this is what gives rise to the neutrinos. So when I form pairs, one of the pairs contains the neutrinos, and this is then what gives rise to the leptons.
Yeah, Jose, please go ahead.
Yeah, hi again. I have a question and a comment. The comment, let me begin with the comment. It's probably irrelevant, but since we're doing some numerology, that number 32 reminds me of the SO32 string. That's it. I said it was going to be irrelevant. So,
well, I don't know.
Yeah, I said it was an irrelevant comment, but I thought I might just as well make it.
So you mean here you have this SU32?
No, SO32.
SO32.
The SO32, or the spin 32 string.
In fact, like a group which comes up here more naturally is like this SU1616. This is really like the gauge, the local gauge group, the local gauge symmetries. That's the isometries of the spin inner product. This gives here SU1616.
Okay. Anyway, that was my comment was probably wrong.
Yeah, I mean, I don't know if this is how to make use of this SU1616 or SO32 at this stage.
Okay, I hope my question is more interesting. I know you get the Einstein equations. Can you comment plus corrections? Can you comment on the structure of those corrections? What kind of stuff do you get there? Do you get some indication of about the existence of a Planck length, for example, some indication about the possible granularity of space-time? Can you comment on that, please?
Okay, good point. Maybe now I really need to go here to this paper. I mean, so what we know is that, well, we have, of course, so what we know is that we get the Einstein equations. So this is kappa times tjk plus, and then there could be, I mean, the whole setup is diffeomorphism invariant, so it must be curvature corrections. And there could be then terms which are higher order in the Riemann tensor. And we don't know how they look like. And of course, they have to come with corresponding powers. By the way, did I put the kappa on the right side? I always get mixed up. I mean, in any case, I mean, this additional factor has to come, let me think, with something like Planck length square to get something. So in other words, you get powers of this.
Okay.
So therefore, these corrections will be extremely small. And it's also kind of clear that there will be such corrections, but we haven't computed them in detail.
So could I make a comment, Felix and Jose? There is a speculation that when you bring in octonions and try to make, a Lagrangian and octonionic space or a bioctonionic space, and you could possibly relate it to the octonionic projective space. Unlike for the other division algebras, there are no allowed octonionic projective spaces higher than 2. OP2, the octonionic projective plane, is the highest allowed projective space. That seems to suggest that the theory is in some sense exact at the quadratic level, and there may not be higher order correction. That's speculative.
Okay.
Share that thought with you. If you were doing this with quaternions or complex numbers, yes, then you have CPN or HPN with n going to infinity, but not with the octonions. Somehow that's very interesting.
So you would expect that maybe the quadratic term here vanishes. So maybe that this year,
the
factor will be 0.
Yes. The leading order term is all that you have. It is a bit like saying that the Planck scale is reset, say, to the electroweak symmetry breaking scale, say close to a TeV. If that were true, then, Planck scale quantum gravity is TeV quantum gravity. And between TeV and Planck scale, there's nothing. It's like a scale invariant or conformly invariant theory, and you won't get anything new. That picture might be consistent with the possibility that there are no higher order corrections. Of course, that's not the popular view, because quantum field theory will bring in corrections unless the TeV scale is the Planck scale.
Well, okay. I don't know. I mean, then.
I may be wrong. I just wanted to share this thought with you. So you do get these corrections. And
exactly. I would get this. Well, it would be a miracle if the prefactor comes out to be 0. I mean, I would expect that there are some higher correction terms, but I mean, since they are so small, I didn't really take it seriously. I was not too motivated to go into this because I thought this is going to be so small that it's not going to be detectable anyhow.
Yeah. Go ahead, David. Go ahead, please. I should unmute you. Go ahead.
I was just going to say, field theory is motivated to give quadratic Lagrangian how to get Einstein from a quadratic curvature Lagrangian. I mean, one early example of that is Maxwell, which is nice to look from different. And here you can get Einstein-Hilbert with the cosmological constant from a quadratic curvature term.
So it's hard to understand you, at least. I mean, I can't really hear you well. I don't know what
somehow there's a line problem, David. So maybe I can read out what David has written. Is there's literature on how to obtain the Einstein-Hilbert action from quadratic Lagrangians of curvature. For instance, McDowell-Mansouri gravity is one example. quantum corrections need not modify the classical equations of motion.
Aha.
That's his comment.
Mm-hmm. Mm-hmm.
Okay, yeah. I must say I'm not so I'm not so familiar with this. There's not much I can comment on this, honestly.
Yeah, hey, please. Okay, yes, go ahead, please.
So just from my understanding, so if you include these terms, do you get a modification of Einstein's gravity in some limit?
Yes, I
I
would.
think
Yes, I
you
would
get a
expect
kind
that
of
there are
FR gravity, or
Mm-hmm.
Yeah,
okay.
probably yes. I mean, if, as I said, I mean, we haven't looked at this yet. I mean, suppose you take such a quadratic correction term, say Q equal to 1. So in other words, an additional term which is quadratic to
Mhm.
Riemann squared multiplied by the Planck length squared.
Okay, then it's small.
Then it's of course a tiny correction, but still, say near the Big Bang, it would change things. I would think.
Okay, good. So you have a nonlinear modified gravity theory and modified quantum theory at the fundamental level, basically.
Yes.
Okay.
That's what I would expect. Yes.
Okay, thanks.
So, Felix, in the causal fermion space, is there an effective coordinate system on which I can say the correlators are defined?
And coordinates for do you think of it like
No, it's
space
like it's a
time?
manifold, a non-commutative manifold, say, on which
So do you mean like space time or this space curly F?
I'm talking about the space curly F.
Okay, fine. And let me just quickly go to, let's see, I think this is the basic definition. Oh, sorry. So here we are, exactly. So this space curly F here, this in fact has a manifold structure. In fact, not quite. I mean, if you take the points which have exactly n positive and exactly n negative eigenvalues, they form a manifold, or in the infinite dimensional case, a Banach manifold. So this means there you have charts. And also we worked this out in detail. What seems good is to work with what we call wave charts. So you use all these wave functions as the chart.
Oh, and these are complex numbers? Yeah.
These are complex numbers, yes. So we have something like, well, maybe it works the way it works. We have this capital psi, which is a mapping. Let's see. Okay, maybe I don't write it out in detail. We take a bit too much effort. I mean, in any case, I mean, you have this family of wave functions, and you take those to describe your space-time points.
Okay.
Therefore, variation, for example, a variation of a space-time point, say a vector field, is then described. Say I take a vector field. Say this is in TXF. Say this is then described by delta psi, and this delta psi really that I vary all the wave functions at once, like a variation of the whole family of wave functions at this point x.
And these wave functions are described by complex numbers.
Exactly, they're all complex.
So what if we propose that let us now instead try to describe these wave functions by not by complex numbers, but by quaternions or octonions?
Aha. I see. So you want now this here to no longer to this here should be an element of whatever, the octonions here. Or octonions cross C4 or something like that.
Yes. Just a thought.
Okay, I never thought about this or looked into this.
Because that would immediately bring in the octonions just by the proposal, similar to Cole's, that the basic states are made from octonions. And then that would be a very direct connection with this all the other work on.
Okay, I agree. So this would make a much more direct connection. And I hadn't thought about this. Well, from my naive standpoint right now, I would expect that this changes a lot.
Yeah. Yes. Yeah. Okay. We can think about it. There's a
Okay,
question.
I agree. So this is really different from how I mean, what I explained, because I let the Octonions act on linear operators on the spinners, not on the spinners themselves.
Yeah. Vezo, please go ahead.
Yes. So first, I would like to thank for the interesting talk. It's always stimulating to see a different point of view about physics and different tools. And I have two questions. One is related to what was just discussed. I was wondering why you have to do symmetric, because you already have extra structure in this Hilbert space. Why not self-adjoint operators?
Well, in fact, like symmetric here, what I mean here is really the same as self-adjoint.
Oh, okay. So this is self-adjoint then. Okay.
Exactly, symmetric always on the complex one. So what I really mean is whatever x psi phi is psi x phi.
Okay.
So this is what I mean by symmetric, or the corresponding matrix is Hermitian. So this is like what I have. Exactly.
Okay, thanks. And my other question was going back to what Jandra was asking about the structure of the vacuum. So you explained where 8 is coming, but I'm still not clear how, because the way you wrote it, it's in pairs, but how do you break it so that you have this extra term, which is staying out of the 8 to select the extra one?
Okay,
can you say a little bit more about that?
Sure, just 1 second. Maybe it's best to go back here. Okay, so this is the starting point. I have like these 8 summons, and by hand, I say that one of them is different from the others. And then I plug this into the causal action principle, the Euler-Lagrange equation, and work this out. And then it turns out when you start perturbing the system, then it is preferable to form these pairs in order to keep degeneracies. So therefore, you form pairs. So therefore, this here has to pair with one of the others. It doesn't matter which, because they are all the same. Say this pairs up with this. This then forms the leptons, so the neutrinos here, plus then here electron muon tau. And then the other 6 direct summons, they form 3 pairs. These are then the 3 colors of the quarks. So in other words, this pairing mechanism, this is something which comes out of the causal action principle.
So then if I follow up on that, I mean, what if you start with any other number than 7 and have an extra term like this? I mean, would you get a different thing? So would you get something that...
Well, honestly, I haven't looked at this systematically. For example, I would guess, suppose you take here, 10 direct summons. Suppose here I take 9 instead of 7. Then if you form pairs, then you get like, instead of 3 colors, you would get 4 colors. And then again, the leptons. So in this case, I mean, I would guess that you get SU4 instead of SU3. Now, if you have an odd number of direct summons, then I don't know, because then this pairing no longer works. So this means in this case, you would get something probably completely different. Suppose if I take here 8 instead, then you have 9 in total, then you can't form pairs. And then I don't know, you probably get something completely different.
And this pairing is coming from the choice of the action, is that right?
Yeah, exactly. So this is a consequence of this, of the specific form of the Lagrange.
Okay, thank you.
It's probably good to try to get in Octonions at some early stage, because then, there are things which we don't have freedom for. Like if you look at the group G2, SU3 is a subgroup of G2. So SU4 won't come there naturally. I think you will get SU3 from G2, and then you make this 8 states like Colfury does. So yeah, so and just a thought that if you get in Octonions in at an early stage, then many of these things might start happening naturally.
Sure, definitely. Well, I mean, the way I presented it here, I just showed you how I did it. And then in the end, you see, okay, here you have the number 8, the Octonions act. If you build in the Octonions at an earlier stage, then everything might come out much more naturally. I mean, then maybe there's no freedom to choose this 8 anymore.
It's like if I want to write the Dirac equation, not on a 4D space-time, but let's say on a 10D space-time, then the Octonions come in quite naturally. That I learned from Tavian and Corin's work that the Octonions are very natural for the Dirac equation in 10D space-time, because that's what's related to this exceptional Jordan algebra. That was another question, Felix. And what is the dimensionality of space-time for you? It's always 4, is it?
Yes, at least, I mean, for the systems I considered so far, it was always 4 space-time dimensions.
Mm-hmm.
And well, if you want to describe other space-time dimensions, this would probably also be possible. And in fact, I mean, there's no way to really prescribe the space-time dimension directly. The only thing I can prescribe is the spin dimension.
Mm-hmm. Mm-hmm.
And what one sees, if I take like 4-component spinners or spin dimension 2, and you want to work with Dirac operators, then you can take space-time dimension 4 or 5.
Mm-hmm. Mm-hmm.
And then one can argue that 4 is preferable, because then you have this left-right possibility of this chiral spinners. I mean, if you have 5 dimensions, then basically this gamma 5 or I times gamma 5 would be the 5th Dirac matrix.
Mm-hmm.
So it would correspond to this additional spatial direction. And then then you can't play with left and right-handed spinners anymore, which seems to be of disadvantage if you want to minimize the causal action. But I mean, all these are not, there's no rigorous results in this direction.
Mm-hmm.
So in any case, I mean, taking 4-component spinners suggests that, at least in this case, 4 space-time dimension is natural. If you want to have higher space-time dimension, then if you have whatever 8-component spinners, then you could go to dimension 6.
And so when you no, you finish please first. Yeah.
And well, we haven't studied this yet. So I mean, the only thing I can say, in 4 space-time dimension, I can write down a minimizing measure. And in all other dimensions, I can't do it at the moment.
Mm-hmm.
And since this minimizing vacuum measure is always the starting point for all the computations, this also means that in higher dimensions, I wouldn't know how to begin with the computations.
Okay, thank you. And what I was asking was, when the standard model gauge fields emerge along with the Einstein equations, can I think of the gauge fields as forming this fiber bundle on the space-time manifold? Does that kind of a standard picture is evident?
Yes, so some of the way this comes up, I mean, we have this spinorial wave function. So we have, in other words, we have something like a spinor bundle.
Mm-hmm.
And then the gauge potentials act on this spinor bundle. And then, well, then you can describe them by a new bundle, where the gauge fields or gauge potentials take their values. In other words, they come up as in the spin connection. This is where the gauge potentials come.
So then if I think of the manifold on F space, which you just explained, that somehow has a more underlying structure from which space 4D space-time and the spinor bundle will emerge.
Yes. But this curly F the dimension is much larger. So it's a very high dimensional manifold. In fact, like if the Hilbert space dimension goes to infinity, it becomes an infinite dimensional manifold, Banach manifold. But still you have all these structures, and then once you have space-time, like a subset thereof, then by restriction, you get the corresponding spinor bundle in space-time. In fact, this works even if space-time is not smooth. I mean, then of course it's not a spinor bundle in the usual sense, but it's a topological bundle or whatever. But I mean, generally speaking, I mean, you really get all the structures from the ambient manifold. So then they are inherited, or space-time inherits them just by restriction.
And in one of your slides, you mentioned the CKM matrix that also arises. You mean you're actually able to calculate the parameters?
Oh, yeah, okay, good point. I mean, this is like, so here one gets these mixing matrices, and one even sees that they must be non-trivial. So there must be really a non-trivial mixing of the, say, the isospin up and isospin down components.
But do we know
connected to this SU2 gauge field?
Yes.
Of course, it would be nice to compute specific, compute the values of the matrix entries or get estimates on the matrix entries. But this hasn't been possible so far. So someone gets not enough information. So one gets only like a condition for this matrix, but in an an unspecified basis. And therefore, I don't know how this, I can't really tell you how this is really whatever to the Cabibbo angle or something like that.
But somehow it's probably there in the theory, like you were saying, you know, if we can get to the exceptional Jordan algebra and, you know, study it more carefully, we probably might see things there.
Sure, this is what I would hope, or also something we could explore. I mean, working with these Jordan algebras, I mean, this is also where this mixing matrices come up.
Right.
By acting on these 3x3 matrices.
Yes, Jose.
Yep. Can you hear me? Yeah. Felix, can you tell us anything about the cosmological constant from your approach?
Okay, good question. I mean, like,
ideally, I would be asking you to predict it. I mean, it's already been measured. What can you tell us?
Well, I should say, I mean, first of all, I mean, when we derive these Einstein equations up here, what we get, in fact, is only the equations contracted with a null vector. So we get something like this RJK minus 1/2 GJK minus kappa TJK, and now psi j, psi k is equal to 0 for any null vector psi. It's a bit similar to this Padmanabhan's approach. I mean, I think we discussed this.
Yep.
And doing this, then of course the cosmological constant is undetermined, because if you take here the metric, then the metric contracted with a null vector gives 0.
Exactly.
This is why, from the derivation in the blue book, the cosmological constant is undetermined. Okay, then this cosmological constant, we could come back to our paper, Jose. I mean, so,
yeah,
if we look at this dark matter, dark energy, I mean, we have a mechanism where this comes up also with the right scaling behavior.
Yeah.
But this is a somewhat different approach. In this approach, we start from the usual Einstein equations, and then we study what is the effect of the Dirac sea, taking into account, say, the finite lifetime of the universe, or finite time until the universe reaches a final end state.
Yeah, well, my question was more related to the fact that the cosmological constant in this approach seems to arise, in your approach, seems to arise as a correction term to the original Einstein equations, which is, by the way, also the way it arose historically. But what I find nice in the approach is that the structure of the theory itself allows for some correction. As you pointed out, if you contract the metric with a null vector, that is always going to give you 0. But on general terms, you would have to include that term as a possibility. I mean, lambda
No,
times.
exactly. So there is, in other words, this term is, I mean, there is the free, this term
Exactly.
has to be taken into account with
It
an
has to be
unspecified value of lambda.
Exactly. Yeah. Mm-hmm.
So this is undetermined.
Even if it's undetermined, but it's there.
Exactly, it is there, yes.
But Jose, are you convinced that the cosmological constant is non-zero?
Well, that's what astronomers tell us.
No, I would say
Yes.
they tell us that the universe is accelerating.
Yep.
And then we say one possible explanation is that lambda is non-zero, but there are perhaps other explanations.
Yeah. Well,
You
okay.
need something that mimics lambda.
Okay, I agree with that. I mean,
I'm not suggesting that the cosmological constant is a fundamental field. In fact, I'm pretty sure if it has to be something composite, it can't be anything fundamental. So it is something that mimics or something that produces the expansion of the universe can be, in principle, mimicked by that lambda term. But of course, in the course of time, I'm pretty sure that this lambda will lose its fundamental status and will be reduced to the status of something composite, a composite of others.
Yeah, that's what I was trying to get at. Yes, yes, we agree. Yes, yeah. Please, Heb.
Just a brief comment on this. For example, the R squared terms can also mimic a kind of cosmological constant. It was one of the first inflation theories where they used R squared terms to get, for a brief period at the beginning of the universe, and de Sitter inflation. So if the R squared term would not be so small, it could also mimic to some extent the cosmological constant. Just
Please say what term of
the Riemann squared term. So in the original inflation theories, they used a Riemann squared term to get a de Sitter phase at the beginning of the universe. And if the R squared term would not be so small in his approach, it could also mimic the cosmological constant to some extent.
Starobinsky inflation, you mean? Yes.
Yes. This was just, so maybe it's somehow already hidden here somewhere. That's what I wanted to say. Okay.
So we are approaching our 2-hour time. Any more questions? Otherwise, we could start winding up. Yes, David has a point. David is saying, right, the cosmological constant can effectively come out of quadratic curvature Lagrange. Yeah, I think same point.
Thank you, David.
Right. Michael, are you there?
Yes. Sorry, just unmuting. Yeah. Yes, that was utterly fascinating.
Yeah, right.
Thank you very much, Felix. It was most interesting.
okay, thank you very much.
I learned an enormous amount. Thank you.
Thanks for the talk.
Right. Well, I'll try and get this and the previous two episodes up on the site before next week.
Great, great.
Okay, great.
And remind me, the next session is going to be on the
Next is Cold Fury, May 5th.
That's
May-
right, May the 5th.
May
Yes.
5th, yes. And then Steve Adler, yes. So we have Cold Fury and Steve Adler in May. That should be very interesting, yes.
Right. Okay. Well, I'll certainly have your talks up by then. Hopefully a bit sooner than that. Right. Well, a very pleasant 2 weeks to until we see you again then. All the best.
Okay, so we say bye to everyone. Thanks a lot for coming.
Oh, thanks a lot again to Jinder. It was very nice to give a talk. And
Yeah, thank you. Yeah, great
keep in
fun.
touch.
See you next time. Bye-bye.
Yeah, see you. Bye-bye.